The good news is that we found two great talks to replace it, two 30-minute talks, just to be clear. The first of which is with George Tarnovsky here. He was with us last in 2017, speaking about reversing using X-rays, and it sounds like today's talk is going to be an expansion on that.
Okay, hey, good morning, everybody. Everybody wide awake? Wow, tough crowd. Okay, hey, good morning. So my talk is on reverse engineering using X-rays. This is not software. This is an X-ray machine. So bear with me. I've given this talk before, but there's some new slides, and the presentation is going to be a little bit different. So just bear with me. A lot of it in the beginning is elementary. Everybody's familiar with circuit board construction. Have you had an opportunity to? Does anybody not have an opportunity to assemble or disassemble a circuit board? Wow. All right then. Well, let's get going. Okay, so circuit boards, as you know, come in various sizes and shapes and so on. The complexity isn't evident from the outside view simply because you really can't tell how many layers are there or what's going on, right? So, in this particular paper is based on a Glenbrook Technologies Jewelbox 90 X-ray machine. The slide to your left is the actual X-ray machine with the stage showing where the circuit board is. To the right, this is the stage and the circuit board is placed in there. And this area right here is what's being observed. The machine's quite an impressive machine. It's a live view, not like your dental X-ray. This was me before I used the X-ray machine. So a long time before. No, actually, this is back in 1980, and that. Anybody familiar with an ADM3? No, another old guy. All right. This was that's an 8-inch drive back there, and that was a CPM-based computer we were building for analytical purposes. Anyway, enough of that. So circuit board construction. Circuit boards come in various shapes and sizes, as I mentioned, and outwardly you can't really tell the complexity. What we have here is an illustration of a two-layer, on the left, a simple two-layer board, where you could actually reverse engineer this very simply by holding it up to a light. On the right side, we've got a complex 12-layer board where you have internal plane layers. These layers here, I don't know if everybody can see that. Can you see that, Mark? Oh, you can, okay. So these layers here would actually mask the view if you were to try to backlight it and see what's going on inside. So it's pretty tough to do visually. So common methods of reverse engineering, you've got backlighting, as I just showed you, conductive tracing, mechanical delayering. So backlighting, as I mentioned, works on everything except for multi-layer boards with plane layers where you're not going to see anything. Conductive tracing, now that's a pretty tedious task if you're talking about some of today's technology where if you have a BGA, ball grid array, the pads may not go all the way through, so you don't see all the balls, you don't see all the pads, so you can't make contact to them. Mechanical delayering, that was shown here a couple years ago, and it's rather destructive, totally destructive. You don't have anything left but a pile of dust when you're done with that, but it does work. So that's another method. I choose to use the X-ray, even though it's a little more expensive. So what we have here is we've got backlighting. This illustration on top is a simple two-layer board, and you can see where you could pretty much get through that and determine where everything's connected and reverse engineer that, right? The other two at the bottom, the only thing you can see are the vias, because these are plane layers that cover the entire board for distributing ground and power. So obviously, you're not going to be able to see anything internally. So that's not going to work for you. So here's a Spartan BGA. So in a ball grid array configuration, you can see that the contacts are made here using these spheres or balls. This is a jar of them for replacement. So in this particular case, when it's placed on a board, you're not going to see anything besides possibly just the edge of the device with regard to connections, maybe. Internally, anything within the inside, you're not going to see using just your visual aids. We have here a decapsulated device, compliments of Chris Tarnovsky. Anybody ever hear of him? I didn't think so. Okay, and then this is the same device, but using an X-ray. And the X-ray had to be stitched together. Excuse the poor stitching job, but you get the idea. So X-rays, you see right through the silicon. You don't see any of the features that you see using a microscope. So two different purposes, but both work, they complement each other. So X-rays, almost everything can be revealed. There's hardly anything you can hide. And I'll show you some of the methods of obscuring the view from people, or so they thought. So here's a typical view of a BGA, and what you're seeing here is you're seeing the spheres, the balls of the BGA. You're seeing the via of the circuit board, and then you're seeing the via on the BGA board. And then, of course, the internal bond wires that are making connections to the die, which is edged right here. So is that clear to everybody? All right, I thought so. So moving right along. So this angular view I'm going to skip, but you can see what happens. So here's on the slide to your left, you've got a direct view of a circuit board. If you look at these traces, you're really not going to be able to, it's very difficult to tell where they're going, what layer are they on. But if you have an angular view, as you do on the right side, you can see now there's separation here. You can actually trace out what layer they're going on, and you can see here and here where they step down. This is, for instance, this is on the second layer, this is on the bottom layer, and I think this is on the third layer. So you can get an idea of where they are while you're tracing through. Okay, so here's an example of a geometric zoom. Geometric zoom as compared to an optical zoom. Optical zoom, you have signal to noise degradation. With the geometric zoom, it's not working. Uh-oh. Maybe you're not going to see it. Oh, no. Bear with me for a minute. I can't get the slide to go. This is not a good thing. Well, I guess you're not going to see a geometric zoom. If anybody wants to see it, I'll be glad to show it to you later. The geometric zoom simply means I'm going to bring the target closer to the emitter, to the actual emission, and expose it that way as compared to optically just zooming in, where I'm going to lose signal to noise. Gee, sorry about the, this is not good because I can't do any of the, Anybody know why I can't get these to run on PowerPoint? All you geniuses, nobody knows? Okay. Sorry, folks, I'm not going to be able to show you what I wanted to show you. Oh, this stinks. This really stinks. There's got to be a way you can do this. Sorry? Yeah, I'm trying. I really needed to show this. Alex, you know everything. Oh, what in the world? I can zoom, but I can't get it to play. Okay. Oh, man. Sorry, folks. So what, this is a live slide. It's a video.
Okay, this is a video. Sorry.
No, it's okay, please.
If you want to go back.
Yeah, okay.
You want to exit presenter, add presenter.
Okay. Oh. No. Same thing. Oh, here we go. Ah. Thank you. Yeah. Got out of that one. Okay, so you can see how grainy it is because we're only sampling 16 times. Now, once we get to the final, now we're going to sample 256 times. You can see the signal to noise is improved, and there you are. You can see the bond wires clearly. You can see that that looks like there's a disconnect. Looks like there's a disconnect, but it's not. They're actually bonded to these buses. That's why they're there. But you can clearly see it, which is pretty unique. So I'm going to do this. Here we go. Okay, so we're going to do a trace, and this would be a typical trace. And this is a little more time consuming. That's why I wanted to do this one because it'll give you an idea. We're going to trace this trace. Here we go again. What did you hit the view to make it go? I can't get that to come back. Technical difficulties, I guess. There's no button. Oh, presenter view. Okay. No, don't go away. This isn't it. No, see, this is just going through all the slides. I want to be able to, it was expanded, fully expanded. We were able to do it.
You want to play again the video?
Yeah. Yes. Thank you. Once again, saved. I still don't know how he did it. Okay, so we're going to trace that guy out. Okay, so watch. So this is typical. This is what we would do. So the X-ray is looking at a live view. So the X-ray's on. We're running around. We're looking. We're following the trace. Everybody has the idea, right? It's this guy right here, by the way. Let me get that off of there. So you see over here, it gets pretty convoluted. So you can't really tell. So you got to stop. You've got to zoom. And this would be typical if you're going through tracing a trace to see where things are going for whatever reason. So this area here, it's difficult to see whether if it's making the turn to the bottom or if it's going to the top. So that requires you to zoom in. And again, as we're going through reverse engineering, we run into this all the time where you've got to stop and take a moment and really analyze where they're going. So you have to zoom in a little further. And you can see it got grainy because I had to change the sampling rate. So now it's pretty evident that this goes like this, right? So now we'll continue. And so you can see the bond wires in the BGA. You can see the edge of the die right here and the bond wires. So you're seeing through all of that. We're still tracing. But anyway, this is our final point. That's where we were going. So that would be typical and what we do using the X-ray. Okay, so here's another BGA. Okay, so it becomes cumbersome to actually work with a BGA because not all the connect. If you look at this particular illustration on the left, you notice that not all the BGAs go to a via, any of these vias. So obviously, this one here makes contact to that, so you're able to touch that BGA, that ball. This one here goes directly out, so you wouldn't be able to even detect where it was going. So that's problematic. But in any event, we got through it and we found where it was, and that was a typical job. So here's a situation where this board, this area in yellow right here, is what we'll be looking at. And you can see from the top side, they actually have a plane layer on the top, so you can hardly see anything. Well, you can't see anything besides a few traces where they have another layer. So The picture to the right shows you that it's very, very complicated. There's a lot going on there, but all of that is inside, and it's done purposely so that you can't trace it. Here's some methods of obscuring that really don't do anything with X-ray. You can obviously get around that. So the picture on the top left is it's been covered with epoxy to obscure the design. And using X-ray, we were able to get through, do a reverse engineer, figure out which processor was there, and replicate it and take corrective measures. The picture on the bottom was somewhat of a scam, where you can see the picture to the bottom right is an obvious footprint of a smart card. That was embedded in that epoxy on that board, and that was easily detected with X-ray. The other thing is obscuring it with lead. This was something new that happened where they put a layer of epoxy down, put a sheet of lead in, put more epoxy on top, and tried to obscure the design. And here you can still see through it. It's a little more difficult to see, but you can see and detect it. Also, if you have lead between two pieces of epoxy, you can rip it apart and take it out easily, which we did. This is a rad-hardened device, and you can see through it on the left. You can see the picture. You can clearly see through it. On the right, it gives you an idea of what the device looks like compared to the PC board that it's mounted on. So this is the rad-hardened device here. And it's very difficult even to see that without zooming into it because of the contrast variation. Okay, so failure analysis. That's another reason to have an X-ray machine, right? So in this particular, the picture to the left, it's missing a sphere. So that had to be removed, reballed, replaced. The picture in the center, you can see the shorts. These shorts wouldn't be evident until you power it up. So if you're lucky, there's no smoke. If you're not so lucky, well, that's going to be costly. This picture in the upper right is it's a real problem. So you've got 3 shorts here, you've got 4 shorts here. I mean, this is a mess. In any event, the X-ray, before you power it up and destroy the circuit, or some of the BGAs, we've got BGAs we paid tens of thousands of dollars for. You plug it in and destroy it, it's very painful. So consequently, the X-ray helps you to ensure that everything is correct. Okay, so this is a little problem I'm going to walk you through that we actually had to do. So we've got this Xilinx FPGA. It's placed on this board. All the vias, every ball is provided at a via, so you can hit any signal you think. So I tried to connect it, and I had no JTAG. JTAG response was nothing. There was nothing there. So obviously it wasn't communicating. So the TDI pin, which is this one, was not connected to that via. So consequently, what do you do? What do you do? The board was defective, but I needed to get the information out of the device. So I took a pin vise with the X-ray, with the help of the X-ray, I knew where it was. I took a pin vise and I drilled a hole, touched the ball, gently, of course. That's why I used it by hand, not by a mechanical means like a drill. I'd be through the device. Then I took a pin here, connected to the TDIO, and then made contact to it, and the result was it found the device. And we were able to dump it and get the data that we wanted out of it. And that's it. Any questions? Okay, thank you. We have a question over here. Somebody had their hand up. Oh, there's a question. There's a question here. Okay.
In a CAD program.
Yeah, so the software that's provided with the company allows you to, for instance, reverse image. There are things you can do with the image to help you get better clarity. That's about it. But there's no failure analysis, with the exception of sizes. You can measure sizes. It's a little clumsy. You can measure gap. You can measure space. How much room there is between the balls, for instance, gaps and things like that.
And is it working? Okay. Is there a way to transform the image to a CAD software so that you can work on the circuit diagram again, or do you have to manually do it?
No, manually. This machine is This is a reasonably inexpensive machine. You're talking about between $60,000 and $90,000. So
Okay.
it's not, it's not that sophisticated. It just gets this job done, and that's
Okay.
basically. It's really for failure analysis, for quality control. We didn't spend $250,000, $500,000 on a machine.
Okay, thank you.
Okay. There's a.
Hi, thanks
Hello.
for the talk.
Thank you.
Could you elaborate more on like the optical zoom? Is it done using lenses?
Yes,
using
exactly.
lenses?
Yeah. So the optical, what it is you have a plate that's illuminated by the X-ray on the bottom side. So you have a 90-degree mirror and a regular camera. So the camera has a zoom lens on it, and that's how they zoom. Not the geometric zoom, optical zoom.
Yeah. So bend the X-ray light or the?
No. At that point, it's visual.
Mm.
Yeah. No, the X-ray stops at it actually energizes that platen, and the machine is good to 5 microns. So it's reasonably good quality, with regard to resolution. But now we're finding that even that's becoming challenging with today's technology. So,
Thanks.
yeah. Any other questions? Yes, we have one over there.
Yeah, I saw failure analysis as like one of the uses. Are there other contexts to do this work in?
Are there other what?
Contexts to do this work in?
Sure. Yeah. Well, just in general, verification of placement, like I mentioned BGAs. It's very easy. Has anybody worked with BGAs, placing them? You have. Okay. So you. So okay. So you know the complexity. It's really easy to have the balls short out because there's too much paste, and there's no way to verify that, with the exception of using an X-ray or power it up and see what happens. Okay. Any other questions? Am I missing anybody? No? All right. Thank you very much. Ah.